Hello everyone. Today we are here to discuss a problem from Elements of Chemical Reaction Engineering by H. Scott Fogler. I'll be using the 4th edition, so all of my references will be in reference to that edition. And we'll be taking a look at problem 8-7, specifically part B of that problem. So this is an important topic to cover, as proper sizing and operation of chemical reactors based on the reaction taking place and the kinetics involved with that is a major component of chemical engineering. It is very important to the safety as well as the economic viability of our processes. So we'll take a look at this problem. We'll start with our problem statement. We'll look at what equations are involved with it, simplifying those equations, and then answering the question as the book has asked us to. So let's take a look at the problem statement here. So we are looking at problem 8-7, specifically part B down here. So part B is asking us to repeat part A, but with the addition of a heat exchanger with that UA value and coolant temperature. So part A asks us to plot conversion and temperature profiles. So that is what the end goal of this problem will be, is to plot those profiles. And we're looking at a PFR reactor. A PFR reactor with a volume of up to 10 decimeters cubed and a Kc value of equal to 10, which is at 450 degrees Kelvin. And if we look back to problem 8-6a, which is in the back here, our important information from that is that we have a liquid phase reaction of A plus B goes to C. And we also have an equimolar feed that comes in at 27 degrees Celsius. And our volumetric flow rate is 2, and our initial concentration of A is 0.1 kilomoles per meter cubed. We also are given a table of additional information here that we will be using, so it may be helpful if you have it up if you are following along. So to start off, the first equation that I used was the energy balance. So I got my energy balance equation from T8-1.E in the 4th edition. I know it can be found a couple other places, but that's specifically where I was looking. So that looks like dt dv is equal to UA, which is a constant given to us in regards to the heat exchanger, times by the group of TA minus T, so that's our coolant temperature minus our reactor temperature, plus the negative rate of reaction with respect to A, which we can figure out since we were given that it is an elementary reaction. And that is all multiplied by the negative heat of the reaction at our reference temperature, which those information was also given to us in that table to begin with. So that whole group then is divided by our flow rate of A initially, times by our information about our specific heats. And these, of course, were also all given to us in that given feed of information. But where we go from there is we'll take a look at this equation before we move on to our other equation that we need and simplify the constants as much as possible so we can get this into a more workable version with only one variable that we have to solve for. So I'll put that up on the top of the screen here. So as previously discussed, we know what UA is, that's given, TA is also given. T, there's nothing that we can do to simplify that any further. So as I've said, the first term that we can rewrite is this negative rate of reaction term. So that is the negative rate of reaction with respect to A, and that can be written as K times by Ca naught, so our initial concentration of A, and that's squared as this is a second order reaction. And then that is multiplied by the group 1 minus x, which is also squared since this is a second order reaction with respect to A. And then we include our second term here of subtracting x over kc to account for the reversibility of the chemical reaction. So we'll start with negative Ra. So negative Ra can be simplified a little bit further. We know that negative Ra can be written as negative Ra is equal to K over Kc times by Ca squared. And that's as it was given to us as second order and reversible. So K is our forward rate constant, Kc is our reverse rate constant. And then from there, we want to write that in terms of measurable quantities. So Ca we can't really measure, so we want to rewrite that as a measurable quantity of our concentration of A initially. So that becomes K over Kc, we leave that the same, but then our Ca becomes CaO, and we want to square that because it was squared previously, and we will multiply that by the group of 1 minus x, so our conversion, and we'll square that as Ca was squared originally. So that rewriting of the equation stems back to chapter 2 or 3. So if you have trouble with that, that would be where I would go to review that. But now that we have negative Ra rewritten, we can move on to our next constant. So our next constant that we can simplify is the heat of reaction there. So the delta H of our reaction at our reference temperature. So usually it's written in the book here as C over A times by the heat of C minus B over A of the heat of B minus the heat of A. So a similar version of this equation is available in the book. It would be written for the typical equation that they use of A plus B goes to C plus D. I have simplified it for our reaction of A plus B goes to C. So from here, we have been given all of these quantities. A, B, and C are all equal to 1. Our H of C, HB, and HA were all given in the problem statement, so we can fill this out here as 1 over 1 times by negative 41, and these are all in kcal per mole, minus, again, 1 over 1. This one is a negative 15 kcal per mole, and then minus a negative 20 kcal per mole. So when we simplify that, we end up with negative 6 kcal per mole. And knowing most of our other units are in units of calories, not kilocalories, we simplified this a little further to become negative 6,000 calories per mole. So when we go back and solve for our temperature profile in regards to volume, we'll plug in our negative 6,000 and be careful to watch that negative sign that shows up in the equation. So this will actually become a positive 6,000 when we plug it back in. So now our next step in the problem is we'll look at how do we calculate our flow rate. So we were given our initial concentration of A, and that was equal to 0.1 kmol per meters cubed. And we were also given the volumetric flow rate, which was equal to 2 decimeters cubed per second. And that fits our equation that FAO is equal to CAO times by our volumetric flow rate initially. So we have to begin by doing a little bit of unit conversion here because we want our final answer to be in moles per second. So our initial initial concentration. Sorry, I forgot my O here. Our initial concentration becomes 100 moles per meter cubed. And our volumetric flow rate becomes 0.002 meters cubed per second. So we end up with FAO being equal to 100 mole per meter cubed times by 0.002 meters cubed per second. So that gives us an initial flow rate of A being equal to 0.2 moles per second. So there's nothing further that we need to do with that calculation. That one is done. So our last step in our energy balance is going to be figuring out this last term. So we have two parts of that. So the first part we will look at is that sum of our theta times by our heat capacities. So this portion of our equation is going to be equal to the heat capacity of A plus our theta value times by our heat capacity of B. And that is where our theta is equal to B over A. So in our case, this is equal to 1 as all of our coefficients in our chemical equation are equal to 1. So our CPs are given in that block of given information, and this becomes 15 calories per mole Kelvin plus our 1 over 1 times by 15 cals per mole Kelvin. So we end up with the sum of our theta Cp is equal to 30 calories per mole Kelvin. That's our final answer for that. And then X is our conversion, so that would be something that we would determine or would be given, but we're going to skip past that for right now and calculate our delta Cp hat. So our delta Cp hat is going to be equal to Cpb minus Cpa. So we're only looking at the Cp of B and A because A and B are the only two things entering our reactor. There is no C within our entering stream. So that is simply going to equal to 15 calories per mole Kelvin minus 15 calories per mole Kelvin. So those are both given as stated above. So that leaves us with our delta Cp hat is equal to 0. So we ignored our conversion X there. As you can see now, it will cancel out as it is multiplied by 0. So now we have all of our variables simplified for our temperature profile equation. So we will move on to the second equation that we need to solve this problem, and that is our mole balance design equation for a PFR. So our design equation can come in a few different forms, but the form that I used was dx over dv is equal to negative RA over FAO. And this is equation 2-15 from the 4th edition of Fogler. And so this is what we're going to use to plot our conversion versus volume profile. And as we've previously discussed, we know how to rewrite negative RA from our energy balance, and we also calculated our FA naught as well. So we are kind of done with this equation. We know how to rewrite it. We'll keep it in mind and use it later. We also need a couple more equations here to finish solving this problem, and those relate to how do we solve for K and Kc, as well as the equilibrium concentration. So to start off with our K and Kc discussion, we'll look at K. So we have K at our reference temperature is equal to K at any temperature is equal to K at our reference temperature times by our E to the power of E over R times by 1 over RT reference minus 1 over our temperature of our reactor. So this is equation E8-3.3. That's where I particularly found it in the 4th edition. It's going to be listed a couple different places as well, but that's where I found it, and that'd be a good place to look. And then our Kc is very similar. Our Kc at any temperature is equal to our Kc at a reference temperature. And then that is E times by the group, or to the power of E over R times by, it is not E over R, that is my mistake. It is the change of our heat of reaction times by that same temperature group of 1 over our reference temperature minus 1 over the temperature of our reactor. So this one, I believe, is found in the same table, and that is equation E8-3.4. So those two equations are how we'll solve for K. All of these constants like Kc, our delta heat of reaction we solved for earlier, R can be looked up, E is given in the equation, and then our TOs are also given within our problem statement. So no further simplification of those two equations, but we will substitute in the constants when we go to solve for our temperature and conversion profiles. Lastly, we need to discuss our conversion, our equilibrium conversion. So that looks like XE is how it is defined in the 4th edition of Fogler. And that is going to be equal to Kc, so our reverse reaction constant over the group 1 plus Kc. So this is equation E8-3.13 in Fogler 4th edition. And we are going to substitute in our definition of Kc that we talked about on the previous slide. So now we have all of our equations, all of our constants are defined. We've simplified things as much as possible. If you're following along, you'll have to do a little bit of substitution in here. I have already done that, simplified for us, so we can take a look at our mathematical modeling software to solve this problem. So we have a system of differential equations that will plug into our software, and it'll solve for our concentration and temperature profiles. So I used Polymath. That's what I would recommend using. So here is my Polymath example code. You'll see up top here are our differential equations that we defined previously. Nothing fancy with those, just the equations as discussed from the book. After that are the explicit equations. So these are the equations that we defined for other variables. So Kc with respect to temperature, K as a function of temperature, the rate of reaction with respect to A and its definition, as well as the equilibrium conversion are there. After that, I defined all the constants. So these are either given to us in the problem statement, like our concentration of A initially and E, or we calculated them previously. So our CP values, heat of reaction, those are all in there. And then at the bottom are our initial and final values. So we have to define an initial value for volume. So Polymath knows how to calculate. We need to define a final value. We need an initial value for temperature and then an initial value for conversion. So our conversion starts at 0. There is nothing reacting at the beginning of the reactor, so there is no conversion. Our temperature initial is 300 Kelvin, so that's given to us in the problem statement. And then our initial volume is 0 as well. And then final is 10 decimeters cubed. And then those values are both given to us in the problem statement. So after we have all that typed up and into Polymath, we hit solve and we get our graphs as the problem asked for. So we see here that temperature rises up until a little under 460 there, a little above, and then levels out as the reactor volume continues. And for our conversion, we see it pretty steadily increase as volume increases, but it's not a straight line and it's quite slow here at the beginning. So that is all for the solution. Thank you all for watching.